Welcome back, and this time we're going to talk about how to define the electric field. So when we talk about electric field lines, essentially it's give the directions, but now we want to calculate the magnitude. So this will be my item 3, electrical field. So electric field, as I said before, we're going to use a symbol E to representing that. So you can see here, in the textbook, typically we use capital letter, but in this class, when you handwrite it, you normally use this bar on the top. This means a vector. Okay. So the definition of electric field is written as a special form, and it's also, we need to borrow another concept which we introduced last time called test charge. So let me get started. Suppose in the beginning, at this particular point, I have a source charge, and I use capital letter Q. And the capital letter Q is essentially similar to the lowercase q. It just means that this time we talk about source charge. This source, what really means is the source of the E field. So that's what we call the source charge. So let me put the charge over here. And this is called source charge. Now, in order to find the electric field from this particular source charge, we need to test it, how large the source charge, how large electric field that is. So then around here, we put a small test charge. Let's call it Q0. The dimension of these charges must be much smaller than the distance between these two charges. In this case, the point charge is a good concept. On the other hand, if you have two charges so close to each other, and then you have to understand what actually these charge really represents. In the DNAs or any other materials which we encounter, we have to talk about atoms, directly atoms. For the moment, we are in the classical physics limit. We are saying that the charge dimension is much smaller than the distance between these charges. Now, to define the electric field from this charge, what we do, we use the test charges over here, and then we will measure the force on this charge. And we know that, suppose this is the positive charge, of course, let's just put positive sign there, and suppose this is also a positive charge. So the force on the Q0, let's just use the symbol F0 to representing that. Remember, this is the force on that test charge. Test charge, we use letter Q0 to representing that. So that's our force, okay? Now, how do you define this Q of this E? Well, what you do the following. We are going to define the electric field at this particular point. Now, this time, be careful, we're going to use a special symbol, A, which we called field point. So in other words, I can choose any arbitrary point in the space, but these points are all called field points. You may wonder why we need field points. And the reason is this. If you look at the definition of how the electric field is defined, since the electric field is from Q, so we use a subscript Q to representing that. So now you can see F0 over Q0. Let's just take this as example. We know the amount of the charge, amount of the force on this Q0, which we use the Coulomb's law. Again, we use the Coulomb's law, and we said these both are positive charges. If you take absolute value, it doesn't matter. Now you look at the distance. The distance should be from Q all the way to the test charge. Let's just write them down. Suppose this is the origin, so we put the O here. Do not get confused with 0. This is the origin. Let me write this down to be more precise. So that's where the origin is situated. So now we write this down, the distance between O and, be careful, before this we normally write O and 0, right? Because that's the distance between these two charges. And now we purposely put A here. Remember, but this takes the absolute value since Q0 is larger than 0, so it doesn't matter. Now let's look at the magnitude E. The magnitude of magnitude of E just equals this amount divided by Q0. Did you see I have denominator have Q0? Numerator has TQ0. Now you see what will happen. This equation is the electric field generated by my test charge. Oh, my source charge, Q. So you see there's nothing to do with the Q0 anymore because it's a ratio proportional. It cancels out. If this cancels out, this means the Q0 disappears from my equation. So then in order to identify where this field is, at which point this field is, so we put A over there and just to identify, tell me which location the field that you are interested in. Now, so therefore, it is a wrong question. Let me write this down. To ask how large Q0 is in order to compute E. Do you understand it? Because you see, there's no Q0 at all. So that is the abstract idea, which is that the field point Q, the field point A at this particular location has nothing to do with respect to of the Q0 anymore. So Q0 disappears from our equation. And this is very, very crucially important. So that's how do we define it. So what's the essence? What the essence was that we use Q0 as a tool to find EQ. That's it. We just use a tool. Once we finish using it, we just get rid of this Q0. So nothing in the equation now. And this equation stand alone is just representing the point charge, the field generated by a point charge at point A. And this is the magnitude. This is the magnitude. And of course, we can figure the units as well. Force in the Newton and divided by Coulomb. So therefore, the units is just Newton per Coulomb. And that's the unit of electric field. Shortly, we will introduce another equivalent units, volt per meter, which is the next chapter which you're going to encounter this. But for the moment, just take note on this. And that's how do we define electric field. Remember, this equation only gave you the magnitude. The full definition, we use this equation, and this is for the point charge only. You may wonder what happens if I do not have a point charge. Suppose I have a parallel plate, positive, 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 negative, 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 like this. How do we find an electric field in these kind of situations? In the experiment, you really need to find this as well. What we do the following. We'll first measure the voltage, which is the next chapter which talk about this, how large the voltage that is. We use the voltmeter. And then we know the distance. So the electric field this time, for the parallel plate, let's just put the magnitude here as well. It just equals, should be positive sign because it takes absolute value, delta V over delta X. Suppose this is my X positive x direction. Now, if you are to be more professional in physics textbooks, for our physics majors, we typically write E equals minus delta V over delta X. In next chapter, we will talk about a little more. And the reason I introduced here is just show you why the units, the volt per meter. The voltage is volts. The position is meters. So that's why this is the units of that. So that's how do you calculate these, the electric field in this kind of a situation. And let me emphasize a little bit further. So this equation, this particular equation, let's call it equation number 1. Equation number 1 just tell you how to compute the magnitude, while the electrical field lines, E field lines, to be more precise, field line direction, it tells you the direction of E. And this direction of E, if you look at our equation, is the same direction as a positive charge, the force direction. Let me write this down. The same direction as the force direction experienced by the test charge. Remember, test charge here, we always use a positive charge. The definition, however, it also applies if you use a negative charge. So in other words, we can turn things around. For instance, this equation can be written as the following way. I think your mathematics should be good enough to understand this equation. Essentially, both sides times Q0. So I have left-hand side at F0, which is the force on the Q0. The right-hand side is electric field at point A, which is where the Q0 is situated. And this is the entire definition of that. In next video, I'm going to show you a lot of these exercises on this. Just keep in mind, whenever we encounter the electric field, the test charge disappears. Test charge is our tool. You should not ask how large is Q0. This is entirely different from Coulomb's law. Coulomb's law, we need to ask, you have Q1, Q2. You just have to tell me how large Q0 that is and how large Q1 that is. So that's an entirely different story. Talk to you later.